on we go with something called infinite geometric series. So in other words, what does infinite mean? Well, there you go. It goes on and on and on forever. Geometric means, of course, it has to have some sort of function of R. It has to have a ratio in it. And series, of course, means that every term is going to be just added over and over and over again. So I've got a beautiful series for you right here. There's a geometric. How do I know? Well, let's take this one and this one, okay? So take 2, divide it by the term previous. Look at that. You got 2 over 4. If you reduce that, that's 1/2. Everything's great. That's your R. That's your ratio value. Prove it, okay? Go from 4 to 2. You got to multiply by 1/2. Of course, 4 times 1/2 is 2. Times 1/2 gives you 1. Times 1/2 gives you 0.5. Times 1/2 gives you 0.25, and so on and so on and so on. So this is an example of an infinite geometric series. They are separated by pluses, yes. They are determined by a common ratio, which we just figured out over here beautifully. Okay. Also, the series has no end. That means this goes on and on and on forever. Okay. But I want you to specifically look at this. This is getting smaller and smaller and smaller and smaller and smaller. If you don't believe me, well, look, I can boot up the calculator here. Start on my first number, which is 4, multiply it by 0.5, you get this. Multiply it again by 0.5, you get that, which you see it's getting smaller. Every time I multiply by 0.5, now check it out when I start multiplying like crazy. Look at this. Look at how small these numbers are getting. Look how tiny they are. Look, I suddenly went from 1 over here, right, to 0.5 to 0.25. Now look at this. I'm starting to get my decimals going here. Holy smokes, is this number ever going to start getting smaller? Watch again. Multiply by 0.5. Multiply by 0.5. Multiply by 0.5 again. Look at that. Look how small this number gets. It's getting so tiny that I got a question for you. If it's so tiny, does it really matter? This number is getting so small, and if you keep on going over and over and over again, eventually what's going to happen is that number down here, let's say term 100, is probably going to be so small, it's going to be like 0.00000000000 something, like 7, for example. Wait a second. Does that really matter? That number that is so small, does it really matter? Actually, it would probably be equivalent to dropping a dime in the ocean. That's it. That's how small that number would be. So what happens with that number? Eventually, this number and this sequence eventually approaches 0. That's how small this number gets. So if you think about it, we have 2 different kinds of series now. We have one that we're used to. It's called a divergent one. You remember this. If let's say it has a R of 2. Well, the first one is 1. Times it by 2 would be 2. Times it by 2 would be 4. Times it by 2 would be 8. By 16. By 32. You can see that these numbers are going up, 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 up. When it's convergent, this means the sum doesn't eventually change. What does this mean? It's this one here. Look how these guys are starting big, getting smaller and 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 smaller, so it doesn't change. So by your textbook definition means divergent means it's an infinite number of terms where the sums approach a fixed value. Does not approach a fixed value. So these guys just keep getting bigger and 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 bigger. Where these ones, look, half, a quarter, an eighth. Oh my goodness, the next one would be a 16th. That's really tiny. After that, a 32nd, a 64th. They're getting so incredibly small that eventually it won't matter. There's the difference. Divergent means it's getting bigger. Convergent means it comes closer and closer and closer to 0. Now, my question to you is what happens when you say, let's add these all up? Let's find the sum. Okay, well, let's look at this, for example. Let's look at the difference between a convergent and a divergent series, and we'll see. Look at what happens with you got a divergent. There's 4, there's 8, there's 16. You keep multiplying. 32, 64. Now start adding this. S1, of course, is going to be 4. S2, add these two together, there's your 12. S3, add these three together, okay, you get 28. S4, add these guys together. Look what's happening. You're getting bigger and bigger and bigger and bigger and bigger, right? But check out what happens when you have this convergent series. 4, 2, 1, a half, 0.25, so on. These numbers get so small. Eventually, watch what happens. Here's S5. S5, 1, 2, 3, 4, 5. You get 7.75. S7 would be adding one more term here. You get 7.9. S9, add it more. Look how little difference there is between these two. S11, look at how little difference there are between them. Look at S13. Look at S15. Look at S17. There's almost no difference between these three numbers. Sure, there's a difference way out here in the tenths, hundredths, thousands, 10,000ths, 1/10,000ths of a place. Well, what happens when you get to S100? You know what? I'll tell you exactly what S100 is going to look like. It's going to look an awful lot like 7.99999999999. Okay? So this number actually doesn't increase anymore because the numbers in this sequence keep getting smaller and smaller and smaller. So think about it this way. Best way to think about this, right here. Why does the convergent series eventually have no increase? Consider a bouncing ball, right? Think of a bouncing ball. Here's a ball falling off a table. So if you bounce the ball, eventually it's going to bounce, and it's going to get less and less and less and less and less and less and less until it doesn't bounce at all, and it's just going to roll along the floor. That's exactly what happens. So if you're adding the height, look, the height's this, the height, add the height, add the height, add the height. Eventually, you're not adding any height at all, are you? Because it's rolling along the floor. That's what makes a series convergent.